What you up to?
Oh, not much. Just contemplating inertial reference frames. And my inertial reference framing and reference framing with my first law holds true, where objects either move with constant velocity or at rest.
So, is essentially what you're saying that all initial reference frames are the same?
That's exactly right, Maxwell. You cannot, there's no experiment that you can do to determine in an inertial reference frame whether you are at constant velocity or at rest.
My equations predicted that the speed of light is 3 times 10 to the 8th in all reference frames.
Well, that is quite interesting. That goes against my relativity principle, which states that the basic laws of physics are the same in all inertial reference frames.
Well, in the Michelson-Morley experiment, they also discovered that speed is constant in all, that the speed of light is constant in all reference frames.
Oh, hello. I couldn't help hearing that you guys were stumped by this null result. Just a second. Let me propose 2 postulates that build off of your ideas. First of all, Newton's relativity principle is correct. The basic laws of physics are the same in all inertial reference frames. Secondly, Maxwell's equations were correct as well. Light propagates through space at a constant speed, independent of the speed of the observer or the speed of the light source, the emitter. Okay, now let's take a look at some of the consequences of these 2 postulates that I like to call special relativity.
Whoa!
Let's ask a question about simultaneity. If 2 events are simultaneous to one observer, are they simultaneous to another observer moving with respect to the first? 2 lightning bolt strikes will be our 2 events, and let's assume that both observers are halfway between the lightning strikes. The light from these 2 events will reach the stationary observer at the same time, because it has to cover the same distance to reach the stationary observer. But because the observer in motion will have moved some distance to the right, the observer in motion will see the lightning strike on the right before he sees the lightning strike on the left, because the light has to travel less distance on the right. This means that the 2 events are simultaneous to the observer at rest, and not simultaneous to the observer in motion. It is tempting to ask which observer is correct, but according to the relativity principle, both observers are right because there is no best reference frame. This implies that simultaneity is not absolute, and that time itself is relative. A second thought experiment can be done to show that time passes differently for different reference frames. For this experiment, recall that velocity is distance over time. Now imagine a spaceship flying past Earth near the speed of light. An observer in the spaceship measures the time it takes for light to emit, cross the spaceship, reflect off a mirror, cross the spaceship again, and arrive back at the observer to be detected in the same location. This time interval is called the proper time, and from the diagram can be determined to be 2d over c. The observer on Earth watches the spaceship fly past him and measures the same phenomenon. Since the spaceship is in motion, the light travels a diagonal path and covers more distance. Because light travels at the same speed in all reference frames, the time interval measured by the observer on Earth must be greater if the distance the light travels is greater. Using Pythagorean theorem, we can determine the total distance the light travels. Once we do some substitution, allow v to be the velocity of the spaceship, and combine this equation with the equation for the observer on the spaceship, we can derive the time interval for which the observer on Earth will measure. This time interval is the proper time divided by the square root of quantity 1 minus v squared divided by c squared. Since the velocity of the spaceship will always be less than the speed of light, the denominator will always be less than 1, and the time interval measured by the stationary observer will be greater than the proper time. This result of special relativity is known as time dilation. Time dilation says that clocks moving relative to an observer are measured by that observer to run more slowly, as compared to clocks at rest. The term 1 divided by root quantity 1 minus v squared divided by c squared occurs often in special relativity and is given a special symbol called the Lorentz factor. Lorentz factor will always be greater than or equal to 1 because the denominator will always be less than 1. Time dilation is not experienced in everyday life because the speeds we experience are relatively small compared to the speed of light, which means the Lorentz factor is virtually equivalent to 1, so the proper time and the relativistic time are virtually the same. Time dilation is a phenomenon of more than just thought experiments and has been confirmed by actual experiments with atomic clocks and subatomic particles. Using similar thinking as in the time dilation thought experiment, special relativity can lead us to another interesting conclusion, known as length contraction. Length contraction holds that the length of an object is measured to be shorter when it is moving relative to an observer than when the object is at rest. Notice that length contraction only occurs in the direction of the motion, which means the height stays the same. Mathematically, the relativistic length equals the proper length divided by the Lorentz factor, where the proper length is the length measured by the observer at rest with respect to the object.
Phew, that was a brainful. So what you're saying is that both space and time are also relative to account for the fact that the speed of light is constant?
Yes. Good thinking, Newton. If we put time on the x-axis and space on the y-axis, and then imagine an object at rest, we'll find that an object at rest does not move through space, but it is moving through time still. If we give that object a velocity, then some of its time motion is diverted to space motion. If an object is traveling at the speed of light, then it has no time. And that is to say, it could travel through space for an infinite amount of distance in no time. So, in essence, length contraction and time dilation balance each other out.
Creating a four-dimensional model of space-time.
That's really interesting. Are there any other quantities that are relativistic?
Yes, indeed. Momentum is relativistic as well. In fact, P equals the Lorentz factor multiplied by rest mass multiplied by velocity.
Wait, rest mass?
Yes, mass is relativistic as well. The relativistic mass equals the Lorentz factor multiplied by the rest mass. That means that as velocity increases, mass increases.
So that means that for any object with mass that it cannot reach the speed of light, because then it would require an infinite amount of energy to accelerate it to that speed.
So, kinetic energy is relative, and mass is energy as well.
Yes, indeed. Energy is equivalent to rest mass times c squared. And let me pose a question to see if you guys fully understand special relativity. So imagine a rocket ship shooting out from Earth at 0.9 times the speed of light. And from that rocket ship, a missile shoots out from the rocket ship moving 0.9 times the speed of light relative to the rocket ship. How fast is the missile moving relative to the Earth?
Well, Einstein, before this conversation, I would have said 1.8 times the speed of light due to basic vector addition of the velocities of each of the components. But now that we've had this conversation, I think that there's some catch in the math.
Indeed, you guys are correct. My math skills aren't quite good enough to actually derive the equation, but from my understanding, in a relativistic world, you can't simply add vector velocities.
Yes, so I did derive an equation because my math skills are much better than his. And I've discovered that as velocity lowers, then it can just be simple vector addition.
So, the equations of special relativity, when velocities are lowered, are the same as the classical equations for, I guess, vector addition, in that the classical equations for vector addition are just more of a special restricted case of the broader equations of special relativity.